Here we'll go through the mechanism for the reaction of aldehydes or ketones with Grignard reagents. In the previous video, we covered some reaction schemes with Grignard reagents. So just a reminder, we start with an aldehyde or ketone. We add an organometallic reagent. The organic part of the reagent adds to the carbonyl carbon. That's all done in a polar aprotic solvent, so an ether, for example. Then in a second step, H3O plus or some acid is added, and that forms the alcohol group, that acidic hydrogen is added to the carbonyl oxygen. So we'll go through the mechanism for these steps. So in step 1, we have our aldehyde or ketone. Now remember, in aldehydes and ketones, we have a partial negative charge by the oxygen. The oxygen has a partial negative charge. The carbon has a partial positive charge. Well, when we have our Grignard reagent present, we have magnesium bonded to a bromine, and then a bond to a carbon chain, which we'll represent as an R group. This magnesium to carbon bond also has a partial positive charge, or a partial charge distribution. So magnesium is a metal. It has a positive charge, partial positive, when it is in a compound. And so our carbon here has a negative charge. So in this case, we have positive magnesium, negative carbon for the organometallic reagent, negative oxygen, positive carbon for the aldehyde or ketone. The oxygen with a magnesium present can coordinate to the magnesium. So we've seen this in the past with lithium present. So this is a coordination . And just like that when we had lithium present, so we saw this with the reduction reactions, having the oxygen coordinated to a metal will activate the carbonyl, very similar to protonating that carbonyl oxygen. Okay, so we've activated the carbonyl. We have a partial negative or formally negative carbon in the organometallic reagent. So that carbon and the electrons in the bond, which are more so owned by the organometallic carbon part of the molecule, because magnesium is a metal, this can now bond to that carbonyl carbon, and the electrons in the pi bond will be owned by oxygen. So the result of this reaction, we have our R groups are the same. Our oxygen in the original ketone or aldehyde molecule has owned an extra pair of electrons now, so it has a negative charge. And we've created a new bond to the R group from the organometallic reagent. Then we have magnesium bromide So these intermediates, after this step, we call this set of molecules a bromo magnesium alkoxide. We have the alkoxide molecule, that's the organic part, and then we have bromine and magnesium. Now this whole step occurs in an ether solvent. So an oxygen bonded to two R groups, which is a polar protic solvent, polar aprotic. So that means there are no acidic protons available to protonate that negative oxygen. And we have to do this first step without any protons, any acidic protons present, because they would interact with the organometallic reagent quicker than the aldehyde or ketone would. And so after we've formed that bromo-magnesium alkoxide intermediate, then water can be added to protonate that oxygen, and we get the final product. So second step, which occurs in acidic water, we start with that alkoxide molecule. We have H3O plus present, and so the negative oxygen with that lone pair of electrons can do just a quick proton transfer. And we now have our alcohol product with that R group bonded from that first step. We have H2O after this step, after deprotonating the acidic water, and we have magnesium and Br minus as ions, because magnesium bromide would dissociate in water into its ions. And so the second step occurs in acidic H2O. Now, there are other organometallic reagents that react in similar ways. We won't do the whole mechanism, but I'll show you two reaction schemes to show two other organometallic reagents. So those other organometallic reagents are organolithium, so you'd have some R group with a lithium cation, and another is sodium acetylide. Which is, we've got a sodium and then a carbon triple bonded to another carbon. So these react similarly, where that organic part of the organometallic reagents with a pair of electrons can add to the carbonyl carbon. So here are two quick examples, one with an organolithium. Let's say we have a propane organic part of a molecule with a lithium. We have some aldehyde or ketone. A common solvent here is a non-polar. And then again an acid in a second step. And the same product as if it were Grignard reagents is expected, where that propyl group is now bonded to the carbonyl carbon, and we have an alcohol group where the carbonyl oxygen was. So that's an organolithium reaction, and then a sodium acetylide is We've got our carbonyl, not our carbonyl, we've got our organic reagent, carbon triple bonded to another carbon, charge balance with a sodium. We can add that. Let's do cyclohexanone as our ketone. Common solvent here is NH3 liquid. And then again, we add an acid in the second step, H3O+. And again, we have the carbonyl oxygen is now an alcohol group, and then the carbonyl carbon is now bonded to that acetylide group. So these other organometallic reagents react in the same ways as the Grignard reagents.